Check. 1, 2, check. Hello? This is a new microphone, so hopefully everything is all working and hooked up. Let me know if there are any audio issues, and I will try to fix them. But I think this is working. Let me see. Levels are good. Okay. All right, so today we're going to not play WoW. So I just happen to have this open, and we can remove that text. And unless people just want to see me play WoW at level 30 on a Burning Crusade server, which I don't think people will enjoy too much. So instead, what we'll do is I'm going to go over to whatever the name of this project is, Orange Slice, and we are going to we'll do a quick recap of kind of what we did last time, and then we'll start trying to transfer over so we can see, we can get an allocator up and running, hopefully bring up the other processors on the system, and we might just call it that for the day. We'll see. So I just found out like 20 minutes ago that I just bought a house, so I might be getting phone calls, and if something comes up, I might have to very quickly stop the stream. But other than that, let's get going. So let's first go back into Orange Slice, and let's make sure we're able to build everything and get that environment back up and running, which it should build. I think I updated Rust recently, so that's gonna have to go through and rebuild those things. Alloc is okay, so those are stable. And let me I'm gonna do a Rust up update quickly. When working with Nightly, it's pretty good to update your Rust pretty frequently, because otherwise you might end up breaking things. So, or you might end up writing code that's already broken. All right, so we've got Orange Slice here, and okay. So, core requirements, blah, blah, blah. Oh yeah, we probably shouldn't have this open while the Rust is updating, because the Rust language server integrates with Visual Studio, or Visual Studio Code. But effectively, yeah, we wrote kind of the bootloader. We brought over the bootloader from before. We got a very basic kernel up and running. And what we're gonna try and do here is get virtual memory allocator working, so we can use things like vectors and strings, and hash maps, and just kind of get a good environment set up. And once we have that, we'll try and bring up the other cores and maybe get soft reboot working, because the next stream after this, if we accomplish all our goals, we'll hopefully be working on an actual hypervisor. And if we're working on a hypervisor, then we're going to be doing that on bare metal. And if we're doing it on bare metal, then we need a good dev environment with a way to fast reboot the machine. And the reason for that is just when most of the machines that I work on are servers with IPMI, and a lot of those take about 1 minute to 2 minutes to go through the BIOS process. So 2 minutes every time you build your kernel is kind of a pain. So we're going to try and pretty much every kernel I write, I have a soft reboot feature that will try and get up and running that allows the kernel to be very quickly replaced dynamically. So, all right, we've got this updating. I don't know why the Rust servers are so slow. I thought they used AWS, but I've noticed that these downloads are painfully slow quite frequently, and then they like jump back up. And it's not my internet connection. It's only with Rust that I have this issue. So once that comes through. But how's everyone's days going so far? I'm also going to be able to sing for you guys now that I have a new fancy microphone. I can put on some like harmony. I can pitch up and pitch down here if I have those on. Let's see. Doop 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 doop. Where is it? Test. Whoa. So now I have auto-tune. But anyways, quick question. This is meant to boot a PE only, not an entire OS. I mean, It's kind of hard to answer. That depends on your definition of an OS. I would say that for some definition of OS, this is an OS, but it does boot a PE. I mean, a PE can be your kernel. For example, like Windows has a PE that is its kernel, and I would argue Windows is an OS. But in terms of like, is this going to be an OS that has a user space and applications and all those things? No, it's just going to be kind of a kernel. I try to call these kernels instead of operating systems. But once the hypervisor is in place, then we'll be able to boot things under it, and those will be full operating systems. But this itself is just going to be a tiny little environment that we can do system-level development rather than using a driver. Okay, so if I remember correctly, I actually haven't changed anything since we left off. And I think some of the things, we got everything kind of booting. Cargo run clean. Cargo run. Let's just make sure everything builds with latest Rust. I think there are 2 warnings that we can get rid of. So it looks like alloc has gone stable in 1.3.6. And so we can just get rid of this that feature requirement in both the kernel and in the bootloader. And that will just clean up warnings. I hate having warnings because sometimes you bury some actual pretty useful messages. Rust warnings have caught a couple bugs for me before. Especially like unused variables of like, oh, I wrote in all this functionality and it says it's unused. So, all right. So we should have the bootloader and everything should be working. That's deploying to TFTP. I need to run that TFTP server, which also does DHCP on in this setup. And in the next stream, once we go to hardware, we'll switch over to using my pfSense router to actually pixie boot machines on my actual network. But for now, we're just doing everything in Hyper-V, and it should be pretty easy. So test VM, and we need one more prompt open as admin, and this one's going to be the display for it. And debug console, cargo run, and hopefully everything still works from where I was before, which it should. Nothing has changed. This is why I hate third-party libs. It takes so long to build these things. Anyways, this should now go through, and new serial session. There we go. Orange slice bootloader, and then we booted the kernel. Parameter is that. Parameter. Okay, so what we can do is, now that we're looking at more of the kernel side that we didn't really look at before, we need to make sure that we're passing the right context and information to the kernel that we need from the bootloader. And some of the information that we need to pass to get a basic allocator working is we need to pass to the kernel the memory that the bootloader has available left. So the bootloader requested from the BIOS what memory is available for use on the system. And then what the bootloader actually used some of that memory, so we have to report the amount of system memory that is available minus the information that the memory that the bootloader reserved for itself. So we're just going to make sure that we pass all that information correctly, because we can't make an allocator without that. So if we look here, we will find that, let's see, we download the PE, we set up some of these kernel buffers or copy it from an existing one. We parse the PE, we allocate these message windows, which are used for communicating in my old kernel, which had message passing rather than shared memory. Since this one actually does, since this kernel is going to have shared memory, we're not going to need these message windows, so we're going to start removing some of these things. And let's just make sure, we haven't made any changes. Those are not significant enough, so sometimes I use git for undo. In this case, we're going to start ripping things out, and we're going to replace them as we're going to remove things and work until this stuff builds and runs again. And we're hopefully going to strip out things that we no longer need. I see you also have a solid color background. Yeah, I have like a color scheme for my machines. I use like a solid black background for my workstation, solid gray for my gaming computer, solid red for ones that are for like test VMs that I like need to be careful of what I'm doing in them, or like ones with malware. And Surprisingly, after doing it for like 5 or 6 years, I just by the hue and like color of all the things in Windows or the desktops, I know roughly what I should or shouldn't be doing in this VM. It helps a lot catch me like when I'm 8 RDP sessions deep to not do the wrong things. So in this case, I'm going through to create a new page table, an empty page table for each CPU that could potentially come up on this machine. In this case, I think it's probably 256. Maybe it's 300. Let me see where I define this. That actually might be in CPU. Max CPUs is 256, which is to support my Xeon Phi. In this case, we're not actually going to need to make multiple page tables. So we're going to make just one page table that we're going to use for all of the cores, since we're going to have shared memory. In the case of the kernel is going to be loaded at the same location for all of them, so we're going to load that into the page table. For each CPU, we're going to have to make a stack, which is valid. We won't need a message window. That's for the message passing stuff. And the core information is the information that we're going to pass off to the kernel. And let's see, we won't need the BSP message windows. We won't need any of this because we don't have message windows. For the BSP, create a copy of the physical memory map to pass it to the kernel. This is where we pass along the information to the kernel of what memory is available. Will you upload the recording once it's done? YouTube actually does that for me. You could go back to the start of the video if you want it. They already right now. But it will be automatically up on YouTube immediately once I'm done streaming. In fact, it's available, the whole video is available at all times while streaming, which is actually really nice for the YouTube platform. So here, let's indent that in a bit. So one thing you'll notice, back when I first wrote Rust, I used C comments. So when you see these C-style comments, you'll note that that code is probably about 1.5 years old. Anything with the C++ or like Rust like comments like this is probably written within the past year. So it kind of gives you a good way to date how old some of the sections of this code are. Nothing here is really older than 2 years. So we're going to parse out that PE. We're going to create a page table. We're going to identity map the first terabyte of memory into that page table. We're going to pick a random location to locate the kernel to. We're going to load the PE to that location in this page table. Then we're going to go through all the CPUs. We're going to allocate a stack. In this case, we pick a random address that can fit stack size, which is probably like a meg or something. Yep, 1 meg. We're going to add that memory to, we're going to map that memory in the page table. Here, this is the core information that's being passed to the kernel. If core info is none, this is probably a global. Yeah, it looks like it is. So we have a global here. If it hasn't been initialized, then we initialize it by setting it to a fixed size allocation. Then we get access to that, and then we're just pushing on the core info for each of these things. So we're not going to need stack base. We will need entry is where that is. The page table is the same. Core message windows we can get rid of. Physical memory is still there. Message window can go away. And kernel buffer, that still needs to be there. And this is kind of like this styling a bit more. So I don't think this is going to build anymore. We broke too many things, and we don't fill in the right fields. So BSP message windows and message windows we no longer need. And bootloader struct, we're missing those. So in CPU, we have bootloader struct, and the core message window is gone, and the message window is gone. And, okay. Value moved here. Oh, value borrowed here after move. Okay, let's take a quick look at what we're doing here. So, move occurs because page table doesn't implement copy. Stack base is page table. I feel like rand address should not be consuming that page table. Oh, it's moved there in the previous iteration of the loop. And if we look at that, page table is in this core info structure, which is something I think we define. So I think we can get rid of that page table because we're using one for the whole system. So we're just gonna get rid of that. I don't think I use that anywhere. No field page table and core info 249. So yep, now we can just use page table, which we'll put in a global actually here. We'll do a static mute page table is an option containing, oh, I might want that old string. This. Doop. We're just gonna fill this in. And this is none. So page table here, and we'll just do unsafe page table equals some. Here we'll do assert page table dot is none. Page table already set. This code should only be run in the context of the BSP, so this is not run on all the cores. Page table is equal to sum of page table, and that's gonna move that into there. I think, no field page table there. And that wants page table dot get backing. So here we can do page table dot asref dot unwrap, and blah blah. It is moved there. So here we'll do, since we move it into this global, we're just gonna rebar it here. Page table is equal to a mutable page table dot asmute dot unwrap. And that will get us a mutable reference to that page table, hopefully. And then pe.load. This guy no longer needs that. And use of a mutable static, which is unsafe, but that's fine. So that apparently built. I think there's a good chance that this will triple fault here, but maybe we just got this right first try. Doubt it. Oh, okay. Okay, so yeah, we were able to boot that new kernel, or we were able to strip out all that message window stuff. I'm kind of surprised. All right, well, take it. I will take it. So we've got that now booting. It's doing the exact same thing as before, but we ripped out some of the message window stuffs and we went to a shared memory model. So let's see if I can get this to... What do you guys want? Do you want to bring up multiple cores first? Or, do you want me to bring up multiple cores or work on the allocator first? And I can do either. I don't think it really matters which order I do it in. It's just what people would like to see first. And whichever one we pick first will probably get done for sure today. And then we'll see if we make it to the other as well. So any minute now I might have to sign a bunch of paperwork. So I'm not sure how long I'm going to be able to run this stream for. But, whoops. There we go. I've also kind of changed my formatting of how I write my Rust, so you'll see me throughout this code. I'm going to remove some of these things. I used to put curly braces on the next line, and now I don't anymore. All right, people want the allocator first. People being one person. Oh, someone said cores. Oh, no. Uh-oh. Uh-oh, that's now there's a battle. So let's see. I might be able to bring up cores real fast. Unsafe. And we're just going to see if we can launch all the cores right away. I'm going to go into my old code base of sushi roll. Sushi roll. Sushi roll. There we go. Use more O's. So we just gotta look for this SIPI. I'm really surprised I don't reference that at all. So we might need to bring over our APIC code here. Let's see what we can do here. I wonder if this code is gonna be portable. Let's see what happens. We're gonna go for the YOLO play here, and we're gonna try and get our APIC up and running. Because once the APIC is up and running, we can identify the cores. There is a way that you can just bring up all the cores without without doing anything fancy. So we'll just call a init here in APIC. So we'll do pubmod APIC and we'll call a init. And we're gonna go through this code. If this does work, we're gonna go through this code and show you what we're actually doing in this. Actually, it's not APIC, it's ACPI code. Did I? Yeah, ACPI. Oops. ACPI. APIC is very close. So, let's see. Okay, we got that. And ACPI code. And this will be pubmod ACPI. And we'll do, the first thing we'll do here is we'll do unsafe ACPI init. And I don't think that took any parameters, and then we'll hold. Okay, that's about what I expected. There are no cast copies and no threads. So this is old stuff from my old code. So let's take a look. I'm surprised I don't have safecast. I should. There we go. It's right there. So let me see if I need to pull that into the cargo toml. Boy, these indents are not deep enough. It's really hard to tell where you are in these folders. I guess I can just click on some of these. Here we go. So safecast equals path equals done. Safecast, I think shared. And let's see. Extern create safecast. I shouldn't need that. Why is that not building there? That is for the kernel, right? Yep. Kernel. Let's see. I'm also going to need byte safe derive. So let's just grab what we have in the bootloader here. This cargo toml. We have these two. And we'll just go over to the kernel one and whoop. Ooh, I actually have a new safecast implementation that I might pull in. So I'll take a look. I'm just gonna get this to work first, and then we'll pull in the newer version of safecast. So in this case, we shouldn't need to do extern create. Oh, you know what? I need to say the Rust version is 2018. Let me go find. I forget the syntax for that. Let's see. Where are we going? Here we go. Edition equals 2018. All right, so pretty much everything in this project where there is a cargo.toml, which is all over the place, we want to add edition equals 2018. We'll do it right now for the kernel. And that changes some of the ways that things are brought in. Can't find byte safe. I think because I'd need to do macro use on that. Macro use extern create safecast. Maybe byte safe derive. Okay. So safecast is a library that I wrote that allows me to cast. It allows me to cast between plain old data in Rust, which is a common activity that I do a lot when writing fuzzers. So lab safecast. It's actually public, and this version is more up to date than the one that I use in this code base. But yeah, it effectively allows you to cast between anything that doesn't have padding and doesn't have pointers or anything in it that aren't safe to cast. So basically any plain old data you can convert to any other plain old data. There's cast copy, which makes a copy of it so alignment doesn't matter. I have strict casting that allows me to actually cast and work with the same backing so I don't have to reallocate. So there are a bunch of kind of cool things we can do there. So in this case, that's init APs. There's launch APs. Let's see. Anywhere where we have this thread, we're not going to be able to use that code yet, but I think that's fine. So, and then here, 17. Oh, and then this one for panic. This needs to change instead of that. This should be crate, I think. Okay, and then ACPI, deprecated item, atomic usize init, and this will be now atomic usize new. Since they kind of cleaned up some of these constant things, we're not using CPU at all. And expected one parameter for init, which is the range set of the E820. So first, let's try to print off if we can. So the parameter we're gonna need to cast, the parameter that we're being passed should be a reference unsafe reference deref of param as const, and let's see what we pass in here. I think it's a bootloader struct, unless it's core info, but I don't think so. I think core info is just for local. Here we pass bootloader info. Yes, so that's going to be a bootloader struct. So here, take that mutable, take that, and this should hopefully give us access to the bootloader structure that, let's see if we can print a field from. I don't think I have debug implemented on this quite yet. I do not. So let's take a look at bootloader struct and where, I wonder if I can F12 that. Nope, I can't. So if we look at this, we should have physical memory, which is a range set. I think I might implement debug on that, maybe? Probably not. Nope. And that is going to be a range set, which contains all the ranges. Clone copy. Yeah, I don't want to implement debug on there because that might change the size of my bootloader to be too large. But we can take a look at... actually, there's entries. There we go. There we go. Dot entries, and then this will do X. We'll do this. Range doesn't have debug on it. Okay. For entry in this, so we'll iterate all of the entries, and then we'll print. Let's take a look. Close some of these windows that we're not using anymore. In this case, the entries should have a start and an end. So we'll just print that and that. So this will be entry.start, entry.end. And this should hopefully give me a memory map of this system. We'll see. And this will get us all the memory information. So we're kind of killing two birds with one stone. So this is saying there's memory available at that location up to this address. I was kind of hoping for more entries in here. Let's see if we can up the size of this VM. 6,000 bytes. This will make hopefully there will be a hole here, or at least this range will change. Since nothing changed in the bootloader, hopefully we'll detect that there's more memory now. And there we go. So this looks pretty valid. So this is going to go up to like an ISA memory hole where devices and stuff and your BIOS might be mapped. And then we start once again at the 4 gig barrier up to some amount. So this should, if we subtract these off, these will be pretty close to the, this will be pretty close to the memory use. I think since we reserved 256 megs for stacks, it should be the size in memory minus like 256. We can actually take a look. 1024, we'll boot this up and see how much memory is in use. What does the ACPI do? ACPI is, I forget what it stands for, but it's basically a huge database that the BIOS maintains of system resources. So it tracks how many processors there are, where the processors live, the NUMA locality to different memory banks, how much memory there is. It's kind of the database for everything you need on x86. So it allows your OS to get all the information about the system configuration and how devices and memory and everything's laid out. If you've ever looked at like the device manager in Windows that shows you all the memory ranges and all the IRQ numbers, most of that information is coming from ACPI. Yeah, advanced configuration and power interface. It also has a lot of stuff of how to turn peripherals off and change things to a different like sleep state such that you can get more power efficiency. So it was, I think, originally designed as a way for power savings, and it kind of expanded. I think it was, boy, it probably goes back to like 95, and it's still the main thing that's in use to this day, even on modern EFI or UFI systems. So here we should be able to see this address. Oops. This address +1 minus this is roughly the amount of memory we have available. We gave it 1024 megs. So if we take this address, we'll see we're at 762 megs. 1024 minus that, that's 261. So our bootloader used 261 megs of memory and the BIOS. So it's pretty high, but that's because we reserve 1 meg of stacks for potentially up to 256 cores. So if we change that num cores number, that would drop down, but I'm not too concerned because this will be running on things with 256 cores. So, okay, so we should be able to then go to ACPI, and we should be able to pass the param dot, I think ACPI expects a range set. And ACPI is going to try and figure out all of the nodes that are available on the system, and if this works, we'll talk through what's actually occurring here. So, yep, that takes a reference to the range set, which is, I forget the name of the field, phys memory. And right now we're doing this for all cores, but we're not bringing cores up yet, so we don't have to worry about it quite yet. All right. There we go, detected 1 CPU, which should be accurate. And then if we, let's change this to like 3 or something kind of weird. And we should be able to see detected 3 CPUs. There we go. So that looks good. Everything's pretty much the same. The amount of memory has been detected based on the nodes. So that's gonna go through and, God, I'm really happy that I was able to just drop that file and it worked. So let's talk about what's going on in ACPI. So in this file, we're going to call init here, and this is going to kind of initialize the ACPI subsystem, which will do a lot of things. So we've got a couple globals here. We have APICs and nodes. So APICs are the advanced programmable interrupt controllers, and for each logical processor on your system, so each hyperthread or whatever, is going to get a different APIC, and that's where you manage your interrupts and everything for that core. But there's also convenient things like timers and other things, but the APIC identifiers are actually how you bring up other cores. So we're going to use the APIC to send an interrupt to cores that are not launched yet to bring them online. So we're going to enumerate the APICs, and we're also going to kind of accumulate them in a database here. Then we have nodes, which is going to track the NUMA nodes on the system, so the different regions of memory that have different locality. So in the case of this VM, there's only one node. But if you have a multiprocessor system where you have physically like multiple processors, like a 4 processor CPU socket machine, you'll probably have 4 to 8 NUMA nodes, and that will tell you, so the memory controllers on the CPUs will be hooked up to specific banks of memory. So when you want to access another CPU's bank of memory, you have to ask that CPU for access to the memory, and the latency is much higher. So for accessing local memory to your core is probably about 150 cycles, but accessing it to a remote core or remote node is probably about 250 to 300 cycles. So it's important that we're able to understand where memory is in locality to other processors, such that we can provide, during the allocations, we'll provide you with local memory, which will hopefully be a little bit faster and have lower latency. So we're going to track APIC info, and this is going to have an APIC ID, which is the identifier that we'll use if we want to direct an interrupt to this core. And then we'll also track a node ID, which will associate this APIC, this processor, with a specific NUMA region of memory, a non-uniform memory area, I think is what NUMA stands for. Then for node infos, we're going to have the node ID, which is kind of identifying itself. We're going to have memory, so this is going to identify the memory that is currently available on this node, and then we'll have original memory, which will track the memory that is available on this node at boot time. And basically, if we subtract these two, we'll be able to determine the amount of memory that we have currently used on the system. So now we're going to look at the RSDP. This is actually the main structure where all ACPI configuration occurs. Let me see if I can get some good documentation up. So unfortunately, it's kind of actually hard to find good documentation on the ACPI. So let's see. Yeah, like this is just tiny. But yeah, ACPI is used for battery levels and fan speed and IRQ routing and CPUs and NUMA domains and all these different things. And everything pretty much starts in RSDP, which is the main structure. And that is a structure that is defined by the ACPI specification. This is not a structure that we made up ourselves. It's important that this is packed and has the properties that it has. But as a signature, a checksum, an OEM identifier, a revision number, and an RSDT address that references the RSDT structure, which we probably have defined somewhere else in this code base. So then we have memory affinity. Since this is packed, I think this is another one that is specific to ACPI, and another ACPI standard header. This is the header that goes in front of every table for all the ACPI tables. So they call these things tables in the ACPI land. So this function is a helper function. Let's actually add some documentation. So gets the NUMA node identifier associated with the processor identified by APIC ID. So this is going to go through all of the APICs in our database, and it's going to make sure it's in bounds of our database, and then it's going to get the node ID from that entry. So this is used to kind of get the NUMA node. This is core ID to APIC ID, converts our internal 0 indexed sequential core identifier to its actual APIC ID. So internally we have something called a core ID that is just an atomically incremented variable at boot time, and we're just going to use that to kind of uniquely identify the different processors on the system. But at some point in time, we're going to want to convert that to the actual APIC ID, and we're going to use that. We're going to walk through all of the APICs to identify which core is which. Init APs and launch APs, we're going to skip that for now. Get table, this is going to take a pointer to an ACPI table, and it's going to return off the standard header of that table and then the remaining bytes of the structure. Otherwise, it's going to return an error. So in this case, we're going to try and read that memory. So let's make a comment here. Attempts to decode raw ACPI table based on a pointer. So we're going to read that pointer as a ACPI standard header. We're going to make sure that the size that this header identifies this structure as is less than the standard header that we expect. Then we're going to validate the checksum. So we're going to cast this constant U8 into a slice. So this will just be a slice of bytes for the header length. And then the checksum is pretty simple on ACPI tables. You just sum up all of the things using wrapping addition. And if the value is 0, then it was successful. So in this case, if the value was non-zero, then we know that there was a checksum mismatch. And then we return out the header that we just validated with the remaining bytes after that payload. And I think this could actually potentially be correct, or incorrect, as we, no, that's actually correct. So then here, this is a physical memory allocator that I'm just changing this formatting to kind of what I do in modern Rust now. So attempts to allocate size bytes with alignment on node ID. So this is going to try to allocate physical memory, physical size bytes of this on node ID. And so what it's going to do is it's going to see if that node is valid. If the node is not valid, then we're going to panic hard because this should never happen. If it is valid, then we're going to get access to that node, and then we're going to allocate using the memory on that node data structure. And this will mutably change the physical memory mappings here, or it will mutably subtract the memory that we consumed. So in this OS, we're actually never going to free physical memory. We're going to consume physical memory, and then when we free memory, it will go into a different list. So we'll kind of talk about that in a bit, but we'll have no way of freeing physical memory. We'll only have a way to free virtual memory. Memory stats, this is just going to go through and it's going to accumulate the total amount of memory. So returns the total number of bytes free on the system on all NUMA nodes. So this will go through each NUMA node and it will accumulate the memory that's available and return that out. And then this one finally is where we're going to do all the crazy stuff. So this will identify APICs and NUMA nodes on the system. So here we're going to get mutable access to the globals, the APICs and node databases. We're going to start off that we have 0 nodes, and we're going to start off that we don't have access to an RSDP. So to find the RSDP, there are a couple ways that you can do it. You can either, you can like scan linearly through memory to find it, or there are a couple BIOS fields that will point you hopefully directly at it. So in this case, the specification, the ACPI specification, tells us to grab the address of the EBDA, which is the Extended BIOS Data Area. This is like a hard-coded address that's reserved by the BIOS. We're then going to grab the address that is there, and I think that is a segment, and that's why we're shifting it by 4. I should have made a note of that. And then what we're going to do is we're going to look through 2 different ranges. So the ACPI specification specifically says, look for the RSDP table between the EBDA and EBDA plus 1024, or between E0000 and 100,000 hex. So that's by the specification. And then we convert this magic RSD pointer into just a U64. So this is going to be the signature that we're going to be scanning for in memory. So here we're going to go through each of the ranges, which we have these 2 different ranges in this set. We're going to, let's see, what are we doing here? This should never happen because that is shift 4. So I think what we're doing, yeah, we're just validating that the range is 16-byte aligned. This is just to make sure that we put valid ranges in here. We also make sure that the range is a non-empty range. Then we go through all of the addresses from the low part to the high part. We're walking 16-byte alignment at a time. That is, according to the specification, this table has to be aligned on a 16-byte boundary. We go through there. We're going to compute the number of remaining bytes in the section to make sure we're going to figure out how much room is remaining. We're going to make sure that the size of the we have enough bytes to fit an RSDP. If we don't, then we're going to break out of the loop, which will cause us to go to the next range. Then here, we're going to try to deref this address that we're scanning, we're walking through. We're going to deref that as a U64, and we're going to see if it is equal to the magic. And if it's not, then we continue and we go to the next address. Otherwise, we're going to cast that to the bytes. We're going to make a slice from this address for the size of the RSDP. Then we're going to perform a fold. We're going to compute the checksum. And if the checksum doesn't match, then we're going to continue. And then finally, at this point, we have identified the RSDP. So we found something in the ranges that the ACPI specification told us. We found the signature that is the correct signature. And then we've also validated that the checksum is correct. And at that point, that's as much as we can do. We set this RSDP as the pointer. What do we do here? We set it as, we set it as the pointer to the RSDP. Yeah. And then we break out. So once we break out of that loop, if we were able to successfully identify an RSDP, then we return that out. Not return it out, we bind it to this variable. Otherwise, we return out an error that we were unable the RSD pointer structure, which is kind of the start of all the ACPI work. Then we're going to get the RSDT. So we're going to, in the RSDP, there is an entry that points to the RSDT, which is another table. Let's see. I think my stream just cut out for a second. Let's see if it comes back. I'm going to wait 2 seconds here. YouTube's telling me that my stream apparently cut out. I don't know if it did or not. OBS doesn't. I think I dropped a couple frames, but let me see. My internet may have temporarily dropped. We'll just give this 2 seconds here. Can you guys hear me at all? Huh. I think I have internet. Yeah, my internet seems to be working. It's back. Okay. All right. Sorry about that. I don't know what happened. So then what we do is, now that we know where the RSDP is, that RSDP references the next table called the RSDT. I forget what all of these things stand for. There are so many acronyms. And we're going to use our get table routine, which will correctly identify and validate this structure. We're going to make sure that the length of remaining bytes, so the remaining bytes after the header is mod 4. I can't remember if that was in the ACPI specification. And then we cast it to U32s. Oh, I see why. Since we're going to cast that to a slice of U32s, we want to make sure that it's mod 4. Then we're going to go through each table. So the RSDT kind of references a bunch of other tables. And what we're going to do is we're going to go through each U32 in the RSDT, and we're going to treat it as a pointer to another table. So we're going to try and get access to the table. We're going to get the header and the remaining bytes. So there are a couple different tables that we're going to handle. We're going to grab one, which is the APIC. And I must not have known that you could do a B prefix on these back when I initially wrote this. So if it's an APIC table, then we do this. I think that, yeah, we actually have to do these in order. So we go through the table. We're looking for if it has an APIC signature, then we make sure that the size of the structure, if it's less than 8, then we return an error because this is the MADT, which, gosh, I might need to just get the... So the MADT is the multiple APIC description table, and this describes the different APICs on the system. And these structures are pretty straightforward. It's just, it has the signature, the length, version checksum, so that's the standard header, and then afterwards, it has the local APIC address and then different flags and then all kinds of entries for the different APICs on the machine. So what we do is, let's see, we skip over 8 bytes, which is these first two, the local APIC address and the flags. And then what we're going to do is we're going to go through each 2-byte entry, which are these entries. Are these tables that you are looking for already there from Hyper-V? Yes, it is required that the BIOS is providing this to me. So in the case of Hyper-V, Hyper-V's BIOS must be giving me this information. So first we make sure that the record length, if it's less than 2 or it's greater than the size of the payload, we return an error because that's an invalid record length. If it's a type 0, it's a legacy local APIC record, and that just there are a couple different ones. So this is the local APIC record, and then the IO APIC record, and there are a couple more. This local APIC address override, I think we ignore this, but we might have to use it. So what we're going to do is we look through all the different, we get the processor ID, I think. Is that a processor ID? Yeah, the ACPI processor ID, then the APIC ID, then the flags, which we convert to U32. If the APIC ID is greater than max APICs, then it won't fit in our database because we statically allocate the size. and then we check if the APIC is enabled. So there are flags on here, and the bottom bit tells you whether or not that processor is enabled. And in this case, if it's not equal to 0, which means this processor is enabled, then I'm going to increment the number of cores on the system, and I'm going to then store this APIC information into our APIC database. We're just going to record that we don't know what node this belongs to, and we're going to record the APIC ID for this. Further, for a type 9, which I don't think is referenced here, that means an X2 APIC, which is a more modern on processors probably starting in 2012, 2013. You start to get these X2 APIC records. For machines with greater than 256 processors or cores or threads, it is required that you use the X2 APIC because the original APIC used bytes to index the APIC ID, and the X2 APIC uses 32-bit values. So you can see here we get the APIC ID, which is a byte. We cast it to usize. And here we get the APIC ID, which is a U32. So we have to be able to support the X2 APIC because my Xeon Phi has 256 hardware threads, which shows up, I have to use an X2 APIC, I think, if I want to use more than 200 of the cores. So here we're just doing the same thing as above. We're saving off this APIC information into our database such that we can track that. And then we go over to the next table. So we're doing kind of the same thing as before. We're enumerating all the tables in RSDT. We're going to try to identify the SRAT table. And in this case, we have some notes for some Dell workstation I tried, had multiple SRATs, and the second SRAT was like completely broken. So I made a state machine here that ignores all SRATs after the first one. This is the kind of stuff you get into when you're working with hardware. BIOSes are like, the specifications for BIOSes and ACPI are so loose that people do so many things that are not within spec, and you end up having workarounds like this. But I validate that the table's large enough to be an SRAT table. I grab the payload of the SRAT, so let's see if we can reference it here. So this is the system resource affinity table. It basically tells you what memory belongs to which cores, and also which processors belong to which NUMA regions. So we're going to grab, it's similar as before, there's a type and a record length. We bounds check that. If the type is 0, then it's an APIC affinity structure. So this is assigning an APIC to a memory region like a NUMA node. So we're going to parse out all this information, and they're kind of encoded in a weird way, but effectively we get APIC ID flags and the NUMA ID that this belongs to. We validate all these bounds. If this entry is enabled, then if this APIC does not exist, then we panic, or we return an error saying that we found an SRAT entry that references an APIC ID that is not present on the system. That's a pretty hard error. Here we grab access to the APIC structure, and then if we make sure that the node ID has not already been set, and if it hasn't been set, then we assign that this APIC belongs to this NUMA node. So the reason we have this is it's possible that, yeah, I have a pretty good note here. But this is basically if we have multiple references to the, we return a hard error if there are multiple references saying, hey, this APIC belongs to NUMA node 0, and then they say the same APIC belongs to NUMA node 2. This is pretty pedantic. I don't think it's required. But it's just checking that out. And then here, for an X2 APIC affinity structure, this is similar to before. It's doing the exact same thing as the one above, except for the X2 APIC. Then finally, there's another type, which is the memory affinity structure. And this one's going to define which memory actually belongs to a specific NUMA node. So in this case, we grab, if this affinity is present, then we're going to go through, if this NUMA node has not been recorded in our database, then we're going to set a new entry with an empty set of memory. So there's no memory currently present on this. And what we're going to do is we're going to, let's see, we then get access to that node. So basically initialize it if it's not already initialized. Then here we go through and we add the memory regions that are present in this listing. So this memory affinity structure is going to say physical address 1000 to 2000 belongs to NUMA node 6. So we're going to record that information for NUMA node 6. We're going to insert, so we're going to add memory to available physical memory for this node using these two ranges. And what we do is we track the original and the, so this is going to be the current and this is going to be the original. So right now they're the same. We're just recording them both so we can subtract to 1 to figure out the difference. Finally, if the number of NUMA nodes is 0, which is common on systems with only one NUMA node, then what we're going to do is we're going to make a single NUMA node called 0, and we're going to use the E820 table directly for that. And in this case of Hyper-V that we're running, this is probably what's happening. So this is just an edge case that I saw, I guess, on a Lenovo machine I was working on, and I just needed to basically have some node. And then at this point, I'm going to invert this range set. So I'm going to insert a full-size range. So this range contains the entire address space of physical memory. I'm then going to subtract off the E820, which leaves me with only the memory that is invalid. Then I'm going to go through each NUMA node and I'm going to subtract that off. So basically, I'm performing a union between the memory that the ACPI tables told me and the memory that the E820 that the BIOS told me. And the goal of this is I want the smallest number. If any of them disagree and don't say memory is free, I don't want it. So I only record memory that both of them agree is memory that is available for use. And then finally, this is just statistics. I go through all of the nodes that were allocated, and I print information about the memory that is available for each node, and I accumulate some sum. And finally, at the end, I have this assertion here to validate that the node free sum matches the E820 sum. And this is kind of pedantic. I could potentially drop this since I'm doing a union, but this is to validate that the memory that was reported to me as free by the ACPI tables matches that of the E820. So I'm just looking to make sure everyone's kind of agreeing with what they're telling me on the system. And then finally, we print out the number of CPUs that we detected in this whole process. So that's kind of a run through of this code base. It's pretty basic. There's a lot of things that you can get from ACPI, but this is all I need for spinning up cores and identifying the NUMA locality of different memory regions on the machine. So, does anyone have any questions on this? I have no problem going through and clearing things up and describing kind of what's going on in this ACPI structure. Otherwise, I will start moving over and we'll probably start trying to boot up these other APs. So this is the code that we commented out. This is used to actually launch the processors. And I'm just going to quickly see if I should be able to init APs. We're going to do our APIC. I'm going to grab CPU uplib.rs in CPU. How does this pull BIOS information from Hyper-V with Rust? So ignore Hyper-V. Hyper-V is kind of irrelevant in this whole picture. Hyper-V is just a normal BIOS implementation, so it doesn't matter if it's Hyper-V or hardware or anything, or Zen or KVM. But all of this information was, I found this information by scanning through memory. So there were specific memory regions that I was told to scan through by the ACPI specification, and I tried to identify the ones that had the correct signature. And once I found something with the right signature and the checksum matched, then I was able to make it work. Is there a Rust Hyper-V crate? Nope. This is all completely custom, and none of this is related to Hyper-V at all. Nothing in here is aware of Hyper-V or specific to Hyper-V at all. And then, let's see, APIC ID. So I can get the current APIC ID here. So instead of thread APIC ID, we can just do CPU this, which will query it. So that thread structure, that thread bang, was thread local stuff from my old kernel, and I used that to just cache things before. I'm kind of scared about this. If this builds thread, no thread here, if x2 APIC, so this is fine. None of this is performance critical, so I'm going to quickly use x2 APIC. So if not CPU, use x2 APIC, then that, otherwise that. And we're gonna take a quick walkthrough of this in a second. No comparison between header signature at 291 here. Okay. Blah blah 165. For that, sum.wrapping add. We'll just do an unwrap here. Oh wait, what? Unused return value, that must be used. Sum, is that? Huh, I had a bug. My old stuff had a bug in here. I was not computing the sum. I would always have a checksum match. So let's see if that actually hurts us. There's a chance that that's been broken this whole time. Hopefully we're still good. Yeah, we're still good. Okay. So that was a bug, but luckily it didn't really matter because we haven't seen any malformed ACPI tables. So we should be able to call init APs, and that's going to go through all of the APICs. If the APIC we have identified in the ACPI tables, we're then going to, if it's not ourself, so if it is ourself, we're going to continue in this loop. If it is not ourself, then we're going to determine if we're using the x2 APIC on this machine or if we're using the normal APIC, and we're going to send, this is an init message, which is an interrupt that is sent to another core on the system to tell it to reset to an initial state. And this is doing the same thing, so the 4500 here and the 4500 here. But basically the x2 APIC allows us to index based on 32-bit APIC IDs, and it allows you to do some other fancier things. So the x2 APIC, if we look at APIC right, so the original APIC will write to a shared memory region. The x2 APIC actually writes to an MSR. It's a little bit faster, a little bit cleaner, and so everything's kind of moving over to that x2 APIC model. Then in the launch AP routine, we take a core ID. We look up the APIC ID for that core ID. We then, if it's equal to ours, we panic because at this point we should never request that we launch an AP that is ourself, because that's going to be an issue. Then we go through and this is going to send the init. This is going to send a startup API, and this is going to send another startup API, and this is doing the same thing. So what's happening here with this 8 is that's going to go all the way back to our stage 0, and that 8 is shifted. It's multiplied by 4k. And that is specifically this location. So that 8 identifies the 8th page on the machine, which is this location. And this is where the APs will actually come up, and they'll launch over, similar to what we had before in the first video where we kind of went through this stage 0. But they're going to go into protected mode. They're going to go into the APP protected mode entry, which will go into the into the bootloader, which will be in here. And that will come up. It will get a new core identifier. It will use that core identifier to figure out which stack to use, and it will hopefully go into the kernel as well. So we're going to see, we need to change our kernel quickly. Here, we're going to say if CPU is BSP. So we only want to do this on the bootstrap processor. And then here we'll do our print hello world. So this should still work. We should see one hello world print. And blah, blah, blah. Let's see, how does this look? Okay, good, one hello world print. And here we'll do an expect failed to initialize ACPI. So we weren't checking the return value of that before. We'll just rebuild it and validate that we didn't break anything here. Come on. So, yep, there we go. We were able to successfully do all the ACPI stuff. And now we just have to figure out all of the cores on the machine. So init APs will send an init sequence to all of them. Launch AP will go through each core. So let me see. I should, in theory, be able to do ACPI launch AP 1 and 2. There should not be a 3, but let's see if this works. This is going to be a... I expect this might not work. If it does, I'm going to be really surprised. Oh my god, it worked. Okay, so you can clearly see that we had 3 cores come up, and our print routine does not have a lock. So since there's no lock around our print routine, they all printed at the same time. But you should see 1, 2... There's probably another H in here somewhere. 1, 2... I don't see another capital H. I'm looking for one. It potentially could have gotten eaten. So let's see. 1, 2... Yeah, I don't see the other one. Launch AP 1 and 2, and let's see if we do this. I'm going to get rid of this print temporarily, just to make sure that only the BSP is printing that. But this should hopefully help us out here. Detected 3 CPUs. And, oh, I think I might be able to just call... I wonder if I can call launch AP... Launch AP core ID. I think this silently... Yeah, this will just silently do nothing. So one of these will probably return false. So we'll just go through, we'll launch all these APs, and we'll just do, actually we'll do 4, II, and 0.6. And we don't want to do 0 because that is our bootstrap processor. And we'll just do II here, and we'll print out II. And this will tell us whether or not we were able to try to launch those processors. And there might actually be some, it's possible that these can panic. So it looks like we were able to boot this one, but not the other 3, which lines up with this being a 3-core system. If we change this to be 4 virtual processors, we should hopefully see that a couple of them go through. So let's see what happens here. Yep, true, true, true. So we were able to bring 3 cores up, but and the BSP, so that's a total of 4 cores. So that looks really good. I was not expecting that to work right off the bat, but now we have to change something pretty quick. So this launch AP, we actually want to use on, we want to launch AP1 from the BSP. So we come up, we're running through, we ran through the BIOS, so the bootloader. So the bootloader that we wrote is not thread safe. So it's important that we only have one processor in the bootloader at a given time. So what we're going to do is we have the BSP that launched up, it booted up, it went through the bootloader, and now we're in the kernel. We initialized the ACPI, and now we're going to schedule a launch for the next AP on the system. And then what we'll do is when other cores come up, they will schedule to have the next one boot. So I think this param... let me see if this bootloader struct, and I think this can be constant. I'm just reducing that strictness for now. We'll go and take a look at bootloader struct. That is in CPU, I think. So we have physical memory, soft reboot entry, and a kernel buffer. So I don't have an identifier for the core, so let's just quickly add one here. We'll do static core ID, atomic usize new 0. So what we'll do is core ID is equal to core ID dot fetch add 1 ordering sequentially consistent. So we're just going to fetch the value atomically and then increment it by 1. So this will give us get a unique core identifier for this processor. And we're going to use that throughout kind of the rest of the operating system. And then in this case, we have a convert the bootloader parameter into a reference. Okay, so if we're the BSP, then we're going to init the, and then we can just do this. So, unsafe, attempt to launch the next processor in the list. So this will go through, we're gonna try and bring up the next processor. Eventually there will be a core that doesn't have a next processor to bring up and nothing will get brought up, but this should bring up the next one, and we don't launch an AP until we have successfully gotten to this point. So we'll come through, one core is running, we'll initialize ACPI, we'll launch the next one, we'll halt, the next one will come up, it will launch the next one, the next one will come up, it will launch the next one, and that guarantees that none of the bootloader is in use with two cores at the same time. And then finally we should be able to print, and we'll probably have some spew here again. I need to pull in these atomics, so we'll do use standard core sync atomic use size and ordering. This is required since we're now using that atomic. And then finally, if we go to 99, we'll just do a pointer. Parameter is that. Should be fine, I think. Yeah. Okay, so hopefully all these cores come up. And now we're not having them race during the bootloader, which was probably kind of okay before. So now we see 3 H's printing here. Looks like, actually we have 4. So there we go, we have all 4. So I'm guessing before one is actually getting stuck in the bootloader because they were sharing the stack. But let's do a quick test. Let mute foo is equal to 0. And we're just going to print the pointer of foo. And let's, we need to make our print routine blocked by a spin lock. So here we do our print, and what we're going to do here is, do we manually implement a spin lock or do we make it a generic one? We're just gonna hack it in for now. We'll do static print lock. This will be atomic use size. And this will be atomic use size new 0. And we'll do a print lock. Honestly, we could do an atomic bool. I often do the, I forget what the locks are called when you have one that's incrementing. I'm actually gonna do that. It's more fair. I'm gonna use a fair one. So we'll have a lock here, and we'll have a release here, and they'll both start out the same, and we'll basically get a ticket from the first one. Print lock dot fetch add 1 ordering sequentially consistent. So this will get us a ticket number that is kind of our place in line, and then we'll do while ticket is not equal to print lock rel dot load ordering. We'll just sleep. So basically, we get a ticket, we wait until we are the selected ticket, and then once we're done, we'll update this. So we'll update the ticket to release it, and I think that's right. So they both start at 0. The first one to come will get a 0. That will increment the lock, so the next one will get a higher ticket. It will pass immediately because this will be 0, and then at the end we increment this to allow someone else to come through. So hopefully this will fix our issue with, whoa, we need to move we're gonna move all this stuff up. We'll move this up here. Print, oh. So I think for these modules, we might have to move them below the print. Oh shit. Atomic use size. Oh, I think we have to do it because it's scoped here. There we go. Okay. So let's see if that fixes the race on the prints. Hopefully we see 4 separate lines instead of garble. There we go. So And what we did is we printed off the address of a stack local. So the goal of that was to make sure that these have separate stacks. And if we look, these have all completely different stacks, and we have full system ASLR that will use both the, it will use the addresses in the FF range as well as the 00 range. So that's why you see the differences here. But there we go. We have 4 cores coming up. They have separate stacks, so they should be all good to go. So it's kind of up to us to this point to remember that we have multiple cores running, and we need to be careful not to do anything in a global that is not thread safe. But we are successfully launching those, so let's do cargo run clean. Let's see if we have any build errors. If we have no build errors, I'm going to push this up to GitHub just so we kind of track where this is, or at least make a commit here. Commit am added AP launching, now multiprocessing kernel, and a little smiley face. And let's see if git push works. I might not be logged in here. Nope, I am. So that is already up on GitHub for people who are playing along. So we now have these as separate. So now we can go into writing an allocator. So we have the different regions of, let's see. So we have a way of getting access to physical memory, but we're going to want to construct, we're going to do like a page allocator. So what we're going to do is we're going to request a 4K aligned, 4K size page from the allocator, and we're going to construct virtual memory using those pages. So we're going to allow you to make an arbitrarily sized thing, an arbitrarily sized allocation backed by virtual memory using the physical memory allocator that we already implemented. So let's take a quick look at our, we have, that is in the bootloader. There's a chance that we might already have an allocator here. Okay, so ACPI is where the physical memory is being managed per node. So when we go to allocate, we're going to look up the node ID, or the, we're going to look up the node ID for the processor that's running. So we will want to cache that in a thread local because it's expensive to look that up. But in our testing ground, we're just going to grab that directly out of, we're just going to grab that directly. We're going to get node ID based on APIC ID. So we should be able to do, we're going to scroll here. We're going to print out the APIC ID for a current node. So get node ID for core ID. This will be an ACPI. And this will, I'm going to cargo run. So this will give us access to, this will show us the APIC ID for the processors. Or actually, this is the node ID for the processors based on, I think that needs an APIC ID, not a core ID. So we'll do get APIC ID from CPU. So we'll do CPU get APIC ID, and this will give us the node ID for that one. Here we go. All right, so yep, it has the same result. Still have the same typo from before, which is nice. But you can see we're getting different addresses because everything's ASLR'd, which is nice for, it's kind of nice for debugging. It like hurts debugging when you have ASLR, but it also kind of helps it as well. Let me see. Okay, so, all right. Anyways, so we are going to take a look at, sorry, I just had an email. I'm kind of booked on a bunch of stuff. So I just got my mutual acceptance email saying that paperwork's going through for the house. So I will be a homeowner for the first time well, once I sign that paperwork and send some money over. So I'm pretty excited about that. Anyways, hopefully I'm not too distracted and not too all over the place because I'm now struggling to focus. So we have the node ID that is associated with the current running processor, And we're going to use that in the ACPI implementation to try to get free memory. And I think there might be node alloc in here. So node alloc is going to take a size, alignment, and a node ID, and that's going to give me a pointer or null if it failed to allocate to memory that is in that node. So let's go and we're going to grab the node ID, and we're going to have another pointer here in a second. So we'll do let node ID is equal to this. So we're going to get the node ID based on the APIC ID. Then we're going to cause an allocation. We'll do a node alloc size align node ID. So let alloc equals unsafe ACPI this 4096, and then node ID dot unwrap or 0. So since this is an option, it's possible that we weren't able to get a node ID. In that case, we're going to fall back to the default node of 0. So this will hopefully give us a free physical memory allocation of one page that is 4K aligned in node ID 0, or the node ID of the current core. So hopefully we should be able to see these print. In fact, this is probably going to fail because this is not thread safe. Yeah, this stuff is not thread safe at all. So let me take a quick look. Yeah, so this is written for my old kernel where this was not thread safe. So we need to make note to make this thread safe, but I think for now what I'm going to do is just if core ID is not equal to 0, CPU halt. So this will just be we will halt if we're not core 0. Currently the allocator is not thread safe. So we'll put those in a global that are protected by locks at some point. But for now, we're just going to disable, not disable threading, but make it so only one thread is running. So that should come up. That looks good. And so that was able to allocate physical memory. And so let's start working on a virtual memory allocator. I'm going to need access to the page table. And to do that, we need to implement an accessor for physical memory, which I think I have in the bootloader. So, blah, blah, blah. I think I have to implement this pmem structure, which I think is correct for this one. So we're going to make a new file in this code base called mm. And we're just going to whack this in here for now, and we'll pub mod that. So let's see. Pub mod mm. So bring in the memory manager. Okay. And that's not going to work. So layout is not present. Global allocator is also not present. So we're going to also grab that from the bootloader here. So the bootloader used a full physical memory allocator. It didn't have a global allocator. Cannot be used in submodules. This has to be in the root. So we have to put this up here. And we have to grab global allocator. We'll do that. That will be an mm. Here we'll do pub struct global allocator there. And global alloc is not implemented for global allocator, which is good. So we'll take a look here. So since we already did this in the bootloader, we're going to just kind of steal some of the basic code. And we have to implement these functions to get Rust allocation to work. So we're going to go here. We're going to implement these. And this is not going to work because we don't have these things, so we're just going to delete that. And then for DLX, we're just going to panic. For this, we need global alloc pulled in from, I think that is an so we need that. We're going to need alloc layout, which is here. Whoop. Global alloc. There. And finally, global allocator is not found. We can use crate from here. This will get access to the one in the crate above. finally, global allocator redefined. Whoops. I already had that. There we go. Delete that. Okay. So we already had that. Did you mean that? For global allocator, if we do this, then I think I'm fine. And then for alloc, expected that. So we'll just do core pointer null mute. So I'll get a mutable one, and we're just going to change this formatting up. No free implementation currently. There. Okay. So now what we should be able to do is in alloc, we want to return virtual memory in the current page table. So I think, let's see, oops, what's this going on? Okay, so I need to, let's see, what are we gonna do here? So we're gonna grab this code that we had before. We're gonna get the node ID for the current node. When we go to do an allocation, we have to get the node ID, then we're going to get pages. And for layout, let's see, let size is layout dot size. So this will get me access to the size that wants to be allocated. We're then going to round this up, checked add oxfff, fff, dot unwrap, and not fff. So what this will do is we're going to add fff. This will round it up to the nearest. What we'll also do is if size is less than or equal to 0, so if it's 0, then we'll make size is equal to 4096. So don't allow 0 size allocations. Then we'll get the node ID. So get the current node ID. So far nothing has been thread specific. This is this should be thread safe because this is just an immutable operation. Then we're going to do a node allocation, which is not thread safe, and that's okay. We can just make that safe by saying this is not thread safe. So by doing that, that means the person who calls this will be responsible for ensuring thread safety, which is what we want. We will go over to here. Now what we need to do is we need to pick an address, pick a random 64-bit address to return as the allocation. So this is where we're going to do ASLR. If I take a quick look into how we did that in the bootloader, here we have pagetable.rand adder. And what I need to do is I need to create this page table structure, which will be this. So, get access to the current page table, which is this. Mutable reference to pmem, which is an MMU. Page table, mutable reference to pmem. Let me take a look. That is, yeah, that is this structure. And I guess I have, yep, static mute on that, which I think is fine. So let me go, there we go. We'll make a global for pmem. And what this is doing, this is basically an implementation. This implements the physical memory operations for this system. So this, when we go to work on this page table, it's going to use this alloc page routine. That's then going to, this will get a layout based on 4K. So what I'm going to do here is I have to implement these routines that allow me to read memory, read physical memory, write physical memory, and then check if, let's see, if we reserve memory outside of the page tables. What is this? This is used to let the MMU know if we reserve memory outside of the page tables. We return true, not in the range, not in use of page tables. It's for ASLR. Okay, I need to look into what I use that for. But here I then call global allocator.alloc, which is incorrect. I actually want to do this. So we'll get current node ID. Then we will perform the allocation here. So all we need to do is I need to get a page allocation here. And then if alloc is null, then return none. Otherwise, return alloc as mute u8. So I don't even think I need layout. Yeah, I don't. So get an allocation on the current node. So get node ID, perform an allocation on that node or the 0th node if we don't have a node ID. Then if the allocation failed, then we return none. Otherwise, we will return some with the pointer to the allocation. So that should work. And read fizz and write fizz are correct. So what we should be able to do is we should be able to make this page table structure using pmem. And then we should be able to do almost what we do in the bootloader already, because that technically has an allocator. We're going to do a rand adder, and there we go. So we might already have most of this stuff done. So I'm going to get access to alloc base. We're going to use the page table. We're going to get access to, we're going to use size here. Whoops. Let size equals, actually, I'll just do assert size is greater than 0. 0 size allocation is not allowed. So we round up the size. We make sure that it's not a 0 size allocation. We get access to the page table. Let's see how that works, actually. Then page table, pick a random address that can fit size bytes. Then we add memory for size at alloc base. And I think this, then we can return alloc base as mute u8. Okay, expected to u64. That's fine. And as u64. Okay. Fail to resolve ACPI. That is, here we can do use create ACPI. And alloc not found there. Unused import layout and global alloc. That's main. So here we have layout and global alloc no longer in use. And we have, we're not using global allocator here. And alloc not found, that's fine. Let's, that is main. So let's try and see if we can maybe do an allocation. Let elk is equal to vec new. And that is going to be an alloc vec, I think. Alloc vec new. Foo not found in the scope. Let foo equal 0. Canton for type for t, that's fine. It's a vec of u8s. Yeah. Okay, so we're just gonna pull this in, so we don't need that anymore. We'll just whack that in here. It's kind of crude, but it's just a quick test. There we go. Unnecessary safe blocks in MM. So we have an unsafe in here, which is not necessary. And at 12, where here. Okay. All right. So this is not actually really allocating anything. I think when you make a vector, I don't think Rust is gonna create an allocation yet. So yep, so that's empty, and now this will maybe fail. Let's do elk.push 5. We'll push something onto it, and then we'll print elk.as pointer, and then also elk. So we'll do a pointer, and hopefully this will let us know. I feel like this should not work. I don't know why. Yeah, so that triple faulted, so we did something wrong there. So let's take a quick look at what's going on. So when we perform this push, that will cause this to go to alloc, which will then cause a page table to get created. So let's say, this is going to say print mapped memory at x alloc base. So, oops. So this will kind of hopefully tell us what's kind of going on here. We'll probably see it, yeah, so, oops, don't shut down. So map memory at that. So it was able to find an address, and it was able to map that in. Let's see page table. How does that know what CR3 to use? For pmem, if we look at page table, so backing and physmem, new. Oh, do I do new? Oh, I don't want new. I want from existing, and then I give it a mutable reference to an existing CR3. And in this case, we'll do from existing, and we'll do CPU get CR3. So that would make a lot of sense. I wasn't actually, I was creating a new page table, and I think it might just be CR3. Read CR3? Okay. So we'll do read CR3, and it looks like we correctly mask off the vpid on there, which are some bits at the lower part. So we'll do read CR3, and we'll create a new page table, and as mute blank. So now that will hook up to the correct page table, and let's take a look at these implementations. We have random address, which is going to make sure the size is greater than 0. It's going to canonicalize a random thing based on RDTSC. So it's going to use RDTSC to generate a pseudo-random number. It's going to make that a canonical address, so it's going to sign extend at the 48th bit. We're then going to probe this virtual address, check if the virtual range overlaps with the with an OS reserved range. If we cannot use it, we try a new address. So I think probe virtual address allows me to limit the ranges of virtual memory that's allowed, and then we check kenmap memory, which should go through. It's going to do a translation of that page, and it's going to see if it's valid. So it will basically go through all of the pages to see if we can, or it's going to keep randomly generating addresses until it finds a hole in the page table that's large enough. Then we can do add memory, which will add memory. I think we'll just create RW non-executable memory and fill it with zeros. And we add that to the page table, and we should be able to just do this and run this. And there we go. And we were able to create a new allocation. So that's looking pretty good. Sweet. Yeah, we were able to allocate at this virtual address, and then we had the 5 that we pushed into there. And hopefully we should be able to, we're going to be able to stress this. So what we'll do is I can do for blank in 0 dot dot. We're going to keep pushing a byte onto it until it gets up to a meg. And what we should see is that this should panic because a free will occur, because it's going to try and do a reallocation. It's going to try to allocate a larger size, and it's going to free the old one. So here we see a dealloc attempted. So if we take a quick look at dealloc, let's see if I have any helpers. So if we look at add memory, now that this is working, we can kind of talk about what's happening here. So add memory is going to go to add memory perms, which is read writable, executable, and then I don't know what the last one is. User. Okay, so we're gonna make memory that's read writable, non-executable, and kernel memory, so it's not valid to user space. This will go to add memory perms, which will go up here. It's going to validate that we can map this memory to make sure it's not currently in use. We're going to round the size to the nearest 4K boundary. We're then going to go through each page. We're going to invoke alloc zeroed page, which we implemented in our implementation of physical memory, which is alloc page. And alloc zeroed page is actually a default implementation that just calls alloc page and then zeroes it out. We're then going to convert the bits into the correct page table bits that go. So in the page table, you have a present bit, that's like the bottom bit. You have whether or not it's read-writable all over the place. And we're just converting these booleans into the correct bits that are going to go in the page table. And then we call map page raw on the virtual address plus the offset, so the current page, the physical bits, and then let's see, pt bits, which is the page with everything ORed in. So we take the physical address of the page that we've allocated, we OR in the bits defining the shape or properties of this page, the permissions of this page, and then we're going to do a raw 4 kilobyte mapping at that offset. And this is going to actually walk the page table and do everything for a standard 64-bit 4-level page table. So we're going to canonicalize the address again. We're going to make sure that the address is canonical. We're going to get access to the page table's backing, which is the root page table. It's the initial, it's the highest level in the page table tree. We're then going to check if we're going to make sure it's 4K aligned. If it's not 4K aligned, then we panic. Then we check the mapping. So if we're doing a 1 gig or a 2 meg mapping, so a large page mapping, we make sure that the page table entry that we're trying to fill in correctly has the page size bit set. This is just to make sure that you're doing everything correct. So this map entry raw, you're only using very internally. Then we're going to compute the offsets. So this is going to go through each level of the page table and compute the offset that you'll use to index at the different depths of the page table. So this will tell you for the first level you use this index, second level this index, third level, fourth level. Then we're going to determine the depth of the page table. So if we're using 4 kilobyte mappings, then we're going to have 3 levels of translation. If we have 1 gig, then it's 1. If it's 2 megs, then it's 2. And we just validate that the offsets are 0 for these, because for a 1 gig mapping, it has to be 1 gig aligned, and a 2 meg, it has to be 2 meg aligned. So that validates that the alignment is correct. Then we're going through the page table for all of the depth that we care about. We're going to get the current offset. We're going to read the current entry in the page table at that offset. So we're going to pick the table that is relevant to the address we're translating. And if the entry is 0, meaning that there is no table present there, then we're going to create a new zeroed out page, and we're going to write that in to that entry. So we're going to create a new table at that location. And then we update this cur to the new page table. Otherwise, if there's already a page table, if something is already mapped nearby to this, then we will make sure that it's present. We'll make sure that the page size is 0, and then we'll compute the address for the next level page table and set that to cur, similar to here. So this is allowing us to walk all the way down, creating page tables as the entries do not exist in the page table. Finally, allow remap. So that is the last thing that I pass in that allows me to remap pages. So if we're not allowing for remap, then we make sure that we're able to, we want to make sure that that memory is not already valid. So we're going to try and do a read fizz on that offset to make sure that this entry in the page table is not currently already in use. If it is, then we panic out because we said we are explicitly not trying to map over things that are already used. Then we commit the new entry. And if remapping was allowed, then we have to invalidate the page table entry, the TLB in the processor. We have to tell the processor, hey, the page table has changed. And you might be wondering why we don't do that if we don't allow remapping. And that's because when you convert a non-present page to a present page, you never have to invalidate the page. This is actually a pretty expensive operation, so we only want to do this if we really have to do it. And that's it. That's kind of the whole process of how this allocator works. And we're just going through and grabbing new pages from physical memory, and we're creating a new virtual memory backing using random pages. So if they're all over the place, it doesn't matter, because virtually it will be a contiguous region. And then finally, we don't actually implement deallocation. I might do that, let's see, unmap page. So I think I might already have kind of support if we take a look at this. So if I give it a virtual address, this will allow me to unmap the page of that virtual address. And what this should do is it will go through and try to identify if the entry is in use. If it is in use, then it removes that entry and returns out the address. Yeah. So what this does is it will go through, it will remove that entry, and then it will check if the upper level has any more references in it, and if it doesn't, then it knows that it has to also free those tables. And it always has to invalidate the page table when you're removing an entry, and it updates this free list. So if we call this routine, this unmap page thing here, so we'll do get access to the page table again. If we do page table.unmap page of pointer as U64, I think that expects a U64. Then we'll do a print quickly of what that returns out. And this should be a list of all of the physical pages that are potentially freed during this operation. So let's see. So this is saying that we're trying to free a page. We request that we want to free this specific page. And this is telling us that these addresses can be removed as a result of that page being unmapped. And these are probably the different levels in the page table that are being removed. So we'll be able to add these to a free list in just a second. And let's see here. So unmap page. So we'll want to do assert pointer. We can get rid of this because we're now using it. And we want the layout. So we'll get the size. So similar to before, we're going to get the size. And then we're going to round it up to the nearest page. We're going to go for II and 0 dot size dot step by 4096. So we're going to go through each page in this allocation. We're going to do unmap page of pointer as U64 plus II. And we're going to try and unmap all of those things. And in this case, it's probably only one page for now. Blah, blah, blah. This will convert this to a U64. Let size is U64. Okay, so this will go through each page, and unmap it. Go through each page in the allocation and unmap it. So then this will be the adder. Let adder is equal to this, and we'll do assert adder and OXFFF is equal to 0. Non-page aligned allocation. So we expect that anything that we return from our allocator is page aligned, and thus anything we free from our allocator should also be page aligned. So we're going to panic if it is not page aligned. And then we'll call that unmap page. And here we'll do for page in this. So that we'll call this p page, physical page. Go through all physical pages that were removed, and we'll say if let sum p page equals p page, then add the page to the free list, which we don't have a free list yet, so we'll get to that in a second. 85 blah blah blah. Yes, this is for p page in this. Dot expect failed to unmap. So that returns results. And we just want to do this as well. And this will iterate through. So we'll go through, and this will be want to add X to free list. And we'll just do p page. So this will go through, and hopefully we'll be able to see that it's going to try and free a couple physical pages for the different levels of the page table. Yep, so it wants to add this to the free list, it wants to add this to the free list, this to the free list, and this to the free list. So that is as it kind of traversed through memory and found what is free, it wants to free all these things. So we don't have a free list, so we have to make one. So to do this, we need to So what's kind of tough is we don't actually know what node the memory came from, because we could potentially pass the allocation to another core that then frees it. But we're gonna just temporarily, we're gonna free to the same node. So we're gonna get a node ID. We're gonna have a global, which is a free list. And we're gonna actually put this in ACPI. So up in here, node info, page free list. This will be a U64. And let's see where I allocate node info. This is equal to none. Range set new. This will be page free list. It'll start off at 0, which will be our way of indicating the end of the list. And node info here as well. This will be page free list 0. So we're gonna, the free list is empty as we first start off. Node info here, here. Okay, looks good. And if we go to 87, what is this? That's an MM. So now we should have a way of getting this node info. So node ID, we have a way of looking up. Let me see node alloc. So what I want to do is we're going to make another function similar to node alloc. That's going to be pub unsafe fn node alloc page. And this will take a node ID, allocate a 4 kilobyte page that is 4 kilobyte aligned. So we'll get access to all the nodes and look up the node corresponding to this node ID. Oops. And then what we'll do is if node dot page free list is not equal to 0, then return a page from the free list. Otherwise, this will create a new allocation, and here we just do node alloc. This is U8. So node alloc of 4096 with a node ID of node ID. So if the page free list is not equal to 0, then we have at least one page that we can use. And that page, that will reference a physical address of another page that's currently in the free list. So we will do let cur entry is equal to node dot page free list. Then we're going to read a pointer from it. So we'll do next entry is equal to core pointer read of cur entry as mute U64. We can do a usize. So we're going to read a pointer from that free list, and then we'll do node dot page free list is equal to cur entry, and then we can return cur entry as mute U8. So basically, we will grab the current free list. We will deref the first part of it. So the first 8 bytes, the first quad word of the free list entry has to be a pointer to the next entry in the free list, which could be 0. So if it's 0, then we want next entry. So we will get the current entry. We will then read the next entry. We will update the free list to point to the next entry. And then we will grab the current entry, and we'll mention that this is also not thread safe. And then we'll return the entry that we just popped off the list. So we basically pop something from this stack that we've implemented. So as U64. Okay. So now, instead of using node alloc, we're just going to do node alloc page. And this will now use that free list, which it will always be empty. So let's just quickly double check to make sure we didn't break anything quickly. Okay, come on. So in this case, we want to add all these things to the free list. blah, blah, blah. That's good. So now we need to add a free routine that allows us to push onto that free list. And it's just going to be kind of the opposite of the push that we just did. So in the, where are we at? We want to do that in ACPI. We will do pub unsafe fn node free page, node ID, usize, and then we'll take in a page, which is a mute u8. So add a page to, add a page to the free list. And then we're going to mention this is not thread safe again. So the first thing we want to do here is core pointer right of, so we'll do the same thing as up here. We'll get access to the node specific information. Let the current entry is equal to node.pageFreeList. Then what we want to do is we want to write to the page, the one that we're about to free, a U64, which is the cur entry. So we're going to write the we're going to write in the address of the next entry in the free list to the page that we're about to free, and then we'll do node.pageFreeList is equal to the current entry. Not the current entry. This is equal to page as U64. And that should do it. So we will get access to the node. We'll get the current entry. We will write the address of the current entry into the first slot of the current page. So in the case of the free list being empty, YouTube I might have just disconnected. We'll see. I'm just gonna give this a second. My internet might have, looks like I dropped a couple frames. Okay. Let's see. Come on, YouTube. I don't know if I'm still here or not. It's kind of hard to tell. YouTube is not receiving enough video to maintain quality. I think it's should be going up there. I have internet. Okay, I'm gonna just click on this. Okay, I think we're still good. So basically, if the free list is already empty, meaning this will be 0, then we'll get the current entry as 0. We will then write a 0 to the first part of this page, and then we'll push this onto the free list, which will basically mean there's now one thing on the free list. So now what we need to do is go into our implementation here, and we'll do ACPI node free page of node ID of pPage as mute u8. And then we can also just add another assertion onto here. We'll assert page as u64 and oxfff is equal to 0. Tried to free non-page aligned page. It's a little verbose, but why not? Expected usize found option. So this will be, instead of that, we'll do unwrap or 0. And okay, so casting a reference to a U64 as a mute U8, that's fine. We actually want to deref that. So, and I'm going to put that in parens just to make it a little bit extra clear. And then we should be able to get rid of this, as we now should be deallocating. So a good test of this is to see if we still succeed in our routine. So we'll try this. Let's see if we print, and we should get a meg, so which it might just spew. Yeah, so it's spewing like a meg to the screen, which is good. So one thing that we can do to stress this is just loop. We will make an allocation. We will then push a meg onto it, and then at the end we'll just print this. So we'll do 4 in 0.8192. So basically, we're going to make 8,000 1 meg allocations, which will be 8 gigs. We'll actually go a little bit larger. We'll just go 10,000, 100,000. So this will be allocating 100 gigs, which I don't have in this VM. So if this succeeds, this means we're probably successfully freeing memory and putting it up on that free list. Now let's take a look. And I don't know how long this is gonna take. It hasn't triple faulted. I might have it print a status so I can see like how far it's going in that process. So let's do a quick print. Let's do II. If II mod 10,000 is equal to 0, then print II is this II. So I expect this allocator will be quite slow, but I don't really do much dynamic allocation in my kernel, so I'll just pretty much leave it as this forever. We'll do a special case like slub or slab allocator. So I is 0. I is 1,000. So let's change this to with capacity. So we'll make sure that we pre-allocate it to a meg instead of it otherwise it has to keep growing and doing copies. And then alc push 5, that should be good. We could also do the resize routine if we really wanted. So we're going through. There we go. I is 0, 1,000, 2,000. So by this point, we've allocated, we've allocated more memory than the guest has available. So at this point, we've confirmed our allocator might be broken. I don't think it is, but we are reusing memory. We're not taking new memory from the system. We're just reusing those pages that are in our free list. So, that's pretty much an allocator. The next thing here is we're gonna just need to make this all thread safe. And we're gonna want to do this at this level. And so right now we're just gonna kind of copy and paste the print locks that we implemented, just because they're already done. And we're just gonna whack those in here. This will be CR3 lock, or we'll call it page table lock. And then this will be page table lock release. And we'll move this up to the top. And we'll move this up, and we'll move this and this to the top. Pubstruct global allocator and that. Page table lock. And then here, we'll just grab the same code that we had here. We'll grab a ticket. So that's fine. There's no thread safety there, but the thread safety starts occurring here. We'll do page table lock rel, and then we'll release the lock at the very end. Once we've added memory to the page table and we're no longer using the page table, we can finally do this. So this is not very Rust-like. We would want to actually wrap the page table structure in something that's already protected in some way by these locks. But for now, this will do. So get the tickets. Blah, blah, blah. So basically only one thing can be doing an allocation and working on the page table at a time. And I think that makes everything else safe because we lock at a high level and there's no way that virtual memory allocation can occur while this lock is held. So let's see if this works. I is a 0. And we'll just switch over now to bringing up multiple cores. So now we'll try and hammer it with multiple cores, and it should triple fault pretty hard if they're reusing the same memory. And it looks like they are. We have 4. And this will probably take 4 times as long to get to that. Yep. So we have 4 that have allocated a gig of memory now. So it looks like it should be thread safe as well. So, and we could validate that that lock did something. So sometimes I like to do this where I just remove something that just to validate, like A/B test that without that lock, this should triple fault pretty hard. So let's see. Yep, triple fault. So that's kind of exactly as I expected. So now we have a thread-safe allocator that allows you to do virtual memory allocations, where it constructs new virtual memory allocations based on pages in a free list, and we can free things to the list. So right now it's kind of rough because you are doing 4K allocations for any size. Everything is rounded to the nearest 4K boundaries in both alignment and in size. But in the case of what we need for a kernel, for allocators for this hypervisor that we're going to write, this will be plenty good. So I think I'm going to wrap it up there. We accomplished both goals we wanted to do. We added multiprocessing support, we added NUMA node support, and we added support for a multi-thread safe virtual and physical memory allocators. So I'm gonna just git commit am added virtual memory manager, and we'll just push that off. So thanks everyone for tuning in. Thanks for stopping by. Let me know if you have any questions. I'll stick around for like a minute here to read any questions. For the entry in kernel source main.rs, where does initial input come from? Initial input comes from stage 0.assembly. That is the initial entry point. It's all written in assembly. If I control P, stage 0, it is in the bootloader folder, and this defines the actual entry point of the bootloader itself, which is then passed off to the entry point based on the PE. So the PE file, the executable, references the entry point for Rust, which is the main routine, which I am aware of, and I pass execution onto that entry point from the bootloader. So in here, that's parsed out by the flattenpe.py Python file, and in the case of the kernel main point, that is parsed out by the PE loader that is built into the bootloader itself. If you looked at pe.rs in the bootloader, which is here. So, cool. I think that was a pretty successful stream. That got everything I wanted done in just about 2 hours. So, obviously we reused a lot of code that we had, but I'm pretty happy with this. So, thanks everyone for tuning in. See you later.